Okay, in this video, we're going to continue with our discussion of vectors. We're going to make things a bit more interesting. We now have two operations left to discuss. We're going to take a look at dot products, and we're going to look at cross products. They may seem a bit intimidating at first.
Right.
But
especially if this is the first time you've ever seen it, you might go, whoa, whoa, whoa.
Yeah, slow down. But I promise you guys, first of all, they're not that bad.
Nope.
As soon as you wrap your head around them, the picture will become clear. And you're going to see quickly how important both of these operations are. Let's start out first with dot product.
Okay.
All right, so what exactly is a dot product? Well, we've got two vectors.
Yep.
And what we want to do, really, is find out exactly how much one vector is with another vector.
Exactly.
As weird as that may sound. If you've got one vector pointing in, everybody that's listening to the video, I'll do the following. I want you to take your left hand and point it out straight in front of you. Okay?
Why the left hand?
Good, because I'm left-handed.
Okay.
Now what I want you to do is take your right hand and point it out straight in front of you. Straight, Joel. Okay, we now have two vectors going in the same direction.
Right, they're parallel.
So, how much is one vector with the other vector?
They're perfectly with the other one.
They're perfect. So if they've been normalized, we can say it's 1.
Right.
Okay. Now, keep your right hand pointing forward and take your left hand and go all the way out to the left so that it's perpendicular.
All right.
Now, how much is the left hand going with the right hand?
Not at all.
Not at all if you've got it at a perfect 90 degrees from one another. So this is really, really an important thing.
Right.
And this is also an operation that you guys are going to use so much it's not even funny.
Right. Let's say you have two vectors and you want to calculate the exact angle between them.
Okay.
That's where dot product comes into play.
That's right. Before we really start showing what it looks like, let's give some examples.
All right.
I love examples. So let's start out with, let's do the one where you've got, here's you.
Okay.
And you're looking in this direction, so we've got a vector.
All right. So let's say this is the viewer. This is the eye.
That is you.
And we're looking in this direction, so we have a cone angle, if you will. This is the area that we can see.
So that's our field of view. So you can say there's a line running straight down the center. Look at Joel trying to be all neat. Oh, okay, great. Now, let's say we have an object located over
here.
Over there. Now, let's just say we're writing some sort of code to determine if this object needs to be drawn or not.
Right. And so basically we have a vector that goes from this point, from the current eye, to this point, right? So I would basically have to have a field of view. Let's say this is a field of view of 45 degrees.
Okay.
And to be able to see this, we would have to have almost a 90-degree field of vision to be able to see this
Absolutely.
object. So what we need to be able to do is calculate the angle between this vector that is from the viewer to in front of him to the object over to the side. So we have an angle right here that is, let's say, call this theta, and we want to see whether or not this angle is inside of our 45-degree field of view.
Right.
And in this case, it's not.
It's not, right. But this is a case where you would use dot product to come up with that. Another example, sampling ratio.
Right. Sampling ratio?
Or facing ratio.
Facing ratio.
Facing ratio. What is it?
Facing ratio is basically something where you're looking at a particular object, let's say a sphere.
Okay.
And when you're looking at the center of the sphere, you're looking at a sphere dead on.
Right.
And the center of the sphere, you have a perfect facing ratio. It's 1 to 1.
It's a value of 1.
Right. You're looking straight at it.
And as we start going around the sphere, that value begins to drop.
Drop to exactly 0 when you get to the edges of the sphere.
All the way on the edge. Because at that point, if you were to draw a vector and think about it, how much is going from the center of the sphere out to that point that you're looking at, and then from you going straight forward at the sphere, you've now got a perfect 90 degrees.
Right.
Those two angles are perpendicular. So how much is that with you? 0.
Right.
So you can use dot product for calculating facing ratio as
well.
Right,
and then that's where it becomes really important when writing your own shaders and such.
Exactly.
And if that's confusing to you, which I can understand it being confusing for a lot of people.
Sure.
But once we see some examples in the real world, you'll be able to see it really quickly.
Right. So let's go ahead and start with, let's just make it real simple.
All right.
Let's go ahead and throw up two vectors and show them what dot product looks like.
Let me just erase this real quick here. It was a cool example, but it's gone now.
Yes.
So
two vectors. First one is 1, 2, 3.
So we have 1, 2, 3.
And underneath that, do B vector, and it's going to be, let's say, 3, 2, 1. Woo-hoo. Okay, so first of all, what does this look like? When we want to calculate the dot product, well, it's going to look like A vector dot B vector.
So A
dotted
dot
B.
with a bold dot.
Yeah, so don't confuse that with the multiplication dot.
Yes, it's very, very different because we have two vectors here.
Now, the first thing you need to understand when dealing with dot products is what is the result going to be.
Right, and as we've been saying before, we kept saying it's 1 or 0 or somewhere in between.
Just a number, a single number.
Just a single number.
So it's scalar.
It's going to be a scalar result. So how do we multiply two vectors to get a scalar result? Well, let's go ahead and expand this out to use our vectors here.
Actually, if you don't mind,
I don't mind.
Over here in the upper right-hand corner,
right.
Just represent the following. Let's just do like AX, so like A sub X times B sub X.
A sub X times B sub X.
Put your times back in there.
Times.
All right, so
times.
Now plus. Now we're going to do
A sub Y times B sub Y.
Excellent.
Plus A sub Z times B sub Z.
That's it.
And this right here is equal to A dot
B.
This is the method in which you can actually calculate this area right here, this dot product.
Right. So now let's go ahead and just take our numbers from vector A and vector B, plug them into that formula, and calculate.
So we have our 1, 2. I just like expanding it all out.
Oh, sure.
And then dotted with our 3, 2, 1. And just so you remember, AX is the first, AY is the second, and AZ is the third component, just in case that's confusing. So to put these together, let's just say equals, and AX times BX, so we have 1 times 3, so 1 multiplied with 3, added AY times BY, so 2 times 2, so we have 2 times 2, plus AZ times BZ, so 3 times 1. Now, if we're insulting you with extremely easy stuff, bear with us. This is very, very important to know. So 3 plus 4 plus 3, and this is going to equal 7 plus 3 is 10, so we have 10.
So that is our dot product between these two vectors.
Exactly.
Okay.
So notice we kept saying 1 and 0, and we didn't say that there could be anything greater than 1 or 0.
Right.
Well, in this case, notice that both of these vectors, if we found the length of them, they're not exactly 1, right? They could be, well, in this case, we have 1 plus 4 plus 9, so that's what? 14. So the square root of 14. So obviously this is not a unit vector.
Right.
And this is same for this one as well. So when we're calculating the dot product, we don't always get a value between, say, -1 and 1.
You just said something really interesting. Some beginners with math may have missed this altogether because now you've expanded upon Pythagoras' theory just a little bit, haven't you?
How so?
You want to find the length of A. Before, we only demonstrated finding the length of it with 2 dimensions. But now...
Right. We didn't actually mention how to calculate this with 3 dimensions. It's exactly the same.
It is.
If we just said maybe this one's AX, AY, and AZ, or just X, Y, and Z.
Yeah.
To expand upon Pythagoras' theorem, if I'm saying that right, X squared plus Y squared plus Z squared is equal to, let me just say, L squared, saying the length of it squared. So if I wanted to calculate the length, I would just take the square root of X squared plus Y squared plus Z squared.
And now you'll see why Joel was sitting there saying 1 plus 4 plus 9.
Right.
So 14 and square root of, and so that's exactly what he was just doing out loud a second ago. I just wanted to make sure you guys understood, because you're going to find that, well, for the most part, from now on, we're going to be dealing strictly with 3D.
Yeah.
Every now and then a little bit of 2D.
Right, mostly 3D.
But mostly 3D. So it's important to understand how to calculate a length, if you need one, using an X, a Y, and a Z component.
That's right.
Okay.
So let's see, where were we? Okay, so we have our A dot B, and we calculated this to be 10. So what does this actually represent in another form? So basically, let's write this out. So A dotted with B is equal to the length of A times the length of B.
Again, the times is not to be confused with dotted.
Nope.
Times the cosine of theta.
So this should immediately make it clear for most of you what we've been talking about here. Notice that if A and B or the length of A and the length of B.
If they were normalized,
if they were normalized,
it would just be the cosine of theta.
Right. So let's say we have A hat dotted with B hat. All this is going to equal is the cosine of theta. So that means we can immediately get the angle very, very easily. We can simply switch this around and say arc cosine of A dotted with B, that was a weird symbol, equals theta. So very, very quickly, let me kind of just make this clear here. This is not supposed to be, I'm sorry.
No, that's okay.
A hat.
There we go.
And B hat. Just so people don't go, wait a minute, he just switched his notation around. So yeah, if we take the arc cosine of A hat dotted with B hat, we can get the theta right off the bat. And that's really, really useful, as we were saying before, with phasing ratio, if we're calculating things dealing with light, if we have lighting models that we want to calculate, like Phong or Blinn, which we'll talk about later. I mean, this is very, 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 very important when we want to calculate the angle between two vectors.
Right.
So is there anything else you want to add to that?
Can't think of anything. Just as a reminder, as funny as it may seem, just don't forget, guys, this is gonna be like so basic, but this right here, now I'm writing sideways. This right here is equal to this right here.
Right.
Sometimes for those that are new to this, it's just so easy to overlook that.
That's right. I mean, this right here is calculating the same thing as this is calculating right here.
So they are the same.
So as long as you understand that, I mean, when you're writing your own programs, your vector class or whatever, you're going to probably be using this formula right here to calculate the actual dot product.
Right.
And this is very non-CPU intensive. So when you're calculating dot products and such, calculating the angle between two vectors is very, very simple.
Now, what is absolutely awesome here is if we have two vectors that are perpendicular.
Right.
What's our dot product?
Right. This is a very important concept. What is cosine? Let me just draw a quick diagram of cosine here. It's not going to look excellent, but it's going to be something. So remember, cosine starts of 0, it's going to start out at 1.
The value of 1.
Okay, this looks really bad.
That's okay. Everybody gets the idea.
So it's going to start out at 1, and it has a period of 2 pi. So we have 2 pi at this point. And right here we have pi. So it dips to -1. Remember, cosine goes between -1 and 1. And right here we have our pi divided by 2, which, if you remember, is going to be 90 degrees. So at this point, cosine goes at the top here, dips down, and at 90 degrees it's going to be 0.
Right.
So if we have two perpendicular vectors, let's say we have one vector here and one vector that goes this direction, these are both vectors.
And to make life easy, we'll say they're normalized.
Yeah, we'll say they're normalized with length of 1, in other words, length of 1.
So that basically now we're just left with the dot product
of A hat and B hat, which is equal to cosine of theta right here.
That's right.
Which means at 90 degrees the cosine of theta is 0.
Right. Which is beautiful because as long as you guys keep that in mind, so you can quickly tell with two vectors. Right. You can find out if they are perpendicular from one another, which is awesome. Actually, you can tell from what we've shown you, you can find out whatever the angle is. Right. But in my opinion, I feel one of the most powerful things is being able to check quickly. That it is, that it is indeed 0, because we're about to introduce you guys to cross product. Right. And with cross product, it's beautiful. At the end, when you get your answer, you can then basically take your new vector, because when you do a cross product between two vectors, the result is a new vector. Right. You can take that new vector and you can dot it with either of the other two, and you better get 0. Right. And that's so cool. Yes, and we're about to see why that is. So we want to go ahead and let me just go ahead and erase all of this, say goodbye to all this wonderful math. So, cross product. What is cross product? It is a way of us where we can take two vectors and calculate a third vector that is perpendicular to both of the original vectors. That's right. And remember, if you have two non-parallel vectors, let's just write two vectors right here real quick. Let's say we have one that shoots off in this direction and one that shoots off in this direction. Okay.
if we add these two vectors together, changing their length in one way or the other,
and just keep going with
just go infinitely
all the way around,
you'll notice that we can define an entire plane, which happens to be my monitor right here. It's going to define this entire plane.
That's right.
So with two non-parallel vectors, we can define an entire plane. Now, what if we wanted to find the vector that's perpendicular to both of those?
Right. And for those of you that may be familiar with 3ds Max or Maya or just any sort of graphics in general, you've probably heard the term normal. And we're now showing you how you can calculate the normal of a face. Basically, that's what we're doing here.
I mean, let's just extend this just a little bit. And let's say this is some triangular face. So I'm just going to sketch in a little face here, and we'll call this some face F. All right? And we have these two vectors, A and B, and we have these three vertices, right?
Right.
So vector A goes from this point to this point right here, and vector B goes from this point to this point.
Right.
What if we wanted to find the normal to this face? Because remember, if you're working with 3D applications, you know that you need a normal so that the lighting can be accurately calculated, so you know where the light should shine off of. Essentially.
And if you don't know that, don't worry. We're going to be talking about that a little bit later.
That's right. So if we wanted to calculate the normal to this face, all we need to do is do an A crossed with vector B, and that's going to actually give us a vector that's perpendicular to both of them.
You can say that equals...
you're equals some value.
We can say C vector.
All right, so or we can say N, since we've been using the vector.
Excellent.
So there we have it. So we have a vector that shoots, if I just kind of, something like that, and this is going to be perpendicular to both this one and this one right here.
Yep.
So
that's your normal.
That's right. So you have this normal vector n, which goes exactly perpendicular to both of them.
Now, fortunately for us, figuring the cross product of two different vectors is quite simple.
A little bit more complicated than dot product.
A little. But as long as you understand the formula, it's a shifting formula.
Yep.
That's kind of cool. Then you're in good shape. So here's what I'd like to do.
All right.
We've got, in fact, we can just start where we're at the moment. We've got A crossed with B. Let's give A some values like,
all right, so let me...
vector A is 1, 2, 3, vector B is 4, 5, 6.
Okay, it's 1, 2, 3.
Simple numbers.
It's 4, 5, 6?
Yep, 4, 5, 6. Okay, now putting this together it's real simple, but all right, Joel has got it drawn right now in a horizontal way with the two stacked. So we've got rows and columns. And this is, now go ahead and draw the I, J, and K components above.
Let me just say A crossed with B, and I can write it over here.
Okay.
So A crossed with B. And an easy way to set it up for when you're doing a cross product is to put both vectors together in a matrix type form. So stacked on top of each other. So one giant parenthesis.
Which is what I was kind of hinting at Joel down on the left. But that's cool. He's going to break it up into one big matrix here.
So we have 1, 2, and 3, and 4, 5, and 6. And just end that off in parentheses.
And then we can denote each of the
components.
That's right.
As
I hat, J hat, and K hat.
Let me just move up a little bit. I, J, and K.
Now, remember, in this case, working with cross product, it's different than from dot product, where dot product was returning a scalar. Now we're returning an actual vector.
That's right.
So we're looking for 3 new numbers. And to get these 3 new numbers, for calculating the new X component, if you will, the first thing we're going to do is we're going to disregard the I component in the matrix that Joel has written out up there. So the 1 and 4 will be...
Can I just erase this off?
Absolutely.
Okay.
So the 1 and 4 will be temporarily disregarded, meaning that...
So just pretend this area doesn't exist for a second.
Right.
And then we're going to take 2, multiply that with 6.
Cross multiply here.
And minus that with this vector right
That's
here.
right. So let's go ahead and do it. So it's 2 times 6.
So our first component is our X component. So we have 2 multiplied with 6.
Minus. Important.
3 times 5.
That's
so
right.
we have 3 multiplied with 5.
All right. Now, the next one, actually go ahead and just close off the parenthesis there. I was going to say, just close this off.
I was actually writing it out in vector form.
Okay, that's fine too.
Okay.
The next one now, what we're going to do is we're going to disregard the J component.
Right. So pretend this guy doesn't exist
exactly.
for a minute.
And we cross multiply again. So we're going to do 1 multiplied by 6.
So, but first,
let's do that in a second.
Okay. 1.
So 1 multiplied by 6.
Multiplied by 6.
Minus.
3
3 multiplied by 4.
3 multiplied by 4.
Now, here's the kicker. This is just because of my programming background. Put those in parentheses real quick.
Yeah.
There, I feel better. Okay, now, the y component, you're always going to negate this.
Right.
So put a minus there. Always. This is a common mistake that people make when figuring a cross product.
Right.
Don't forget to put the minus there.
It's very important.
It is only with our y component. You're not going to do it with x, and you're not going to do it with z.
Right.
Okay, so comma.
So we have our comma.
Now we're going to disregard the k component.
So disregard this guy entirely.
So again, we're cross multiplying. So it's going to be 1
times 5 minus 2 times 4.
Ooh, it's so simple.
So 1 times 5 minus 2 times 4 times. Thank you.
Okay, so now let's go ahead and bring this all down.
So we've got 12
minus 15.
Negative
there
6 minus 12.
Nice.
And then we have our 5 minus 8.
Cool.
And then
Bring
if we
it
take
down.
this, we have our negative 3. And then we have a negative 6.
Which means we're just left with... Well, we'll bring that down in a minute.
Yep. And then we have our negative 3.
Right, and in bringing this on down, we've got a vector that's negative 3, 6, negative 3. All right, so, and then just put out, say, equals cross product.
Right.
Or something, just so that
equals A
crossed with
B.
All right, now, this is perpendicular.
Mm-hmm.
This is super awesome.
Yes, it is.
Now what we can do is we can bring what we've learned with dot products into play.
Right, because remember, when we take a dot product of two vectors that are perpendicular, we should get 0.
That's right. Remember what I said at the very beginning of dot products. It's how much one vector is with another vector. How much is he going with them? And in this case, since this new vector, our cross product, should be perpendicular, that means he's not going at all with A or B.
Exactly.
So it doesn't matter which one you do. The bottom line is you should get 0.
That's right.
So now what we can do is let's just pick on A.
All right.
So now we're going to...
well, let's call this N, just so we have a
cool.
vector to work with.
So now we're going to have...
let's do an A dotted with N. And this is going to equal, let's say, our 1, 2, 3. 1, 2, 3 dotted with our negative 3, 6, negative 3. And if we just work vertically here, what we're going to do is 1 times negative 3. So 1 times negative 3 plus 2 times 6. So we have 2 times 6 plus 3 times with negative 3. So 3 times with our negative 3.
Okay,
so this is going to equal
minus 3
plus 12 minus 9.
Yeah, minus 9, excuse me.
So at this point...
You can already see.
What's going on.
Minus 9
so
and minus 3 is minus 12 plus 12
and this
0.
gives us 0.
Meaning that we did it right.
Yes, we did. So A and B are perpendicular, both perpendicular to our vector N.
And again, this is really, really important.
Yes, it is.
Both dot products and cross products are extremely valuable. They're priceless.
Very, very much so.
Formulas for us, and we're going to be using these a lot. So at this point, do not advance until you have a complete understanding
of what's going on here.
Practice them.
That's right. And that brings us to another property of our cross products.
That's right.
So let's come down
about
here.
The magnitude of...
Yes.
Okay, cool.
So let me move up a little bit. Let me. So if we take the magnitude of our A crossed with our B. Let me just write my proper vector notation here. What I have is a value that's equal to the magnitude of A
times the
multiplied by the magnitude of B
times the sine of theta.
Times the sine of theta. So as you can see here, this is a very, very important property to remember because, again, we could use our sine to find the angle of the two vectors in between them, of these two vectors, the angle between A and B, if we wanted to. We simply would divide both sides by the magnitude of A and the magnitude of B, and then we get that equal to sine of theta.
Right.
So again, we could use this, but of course this takes a lot more work than using our dot product. But a nice important side to this is if we could use cross product and dot product to know exactly which quadrant our two vectors are in, so in relation to each other, which also can be very useful.
Sure.
And otherwise, I'm trying to think if there's anything else we need to mention.
That's about all.
Yeah. just remember, make sure this is ingrained inside of your head, because this is very, very important to do. When you implement your own cross product for your own classes that you create, you'll be using this manual method to multiply them and find the cross product, but this relationship right here is crucial and very, very important. Mm-hmm. So I think that's everything. Yep.
So guys, again, review the first video over vectors, review this video over vectors. Both videos covering various operations that you can do between two vectors. Very important stuff.
Yes, very.
And with that, that is going to wrap up this discussion of vectors, and we're now ready to move into matrices.
Yep.
We're going to do that next. Awesome. Okay, so that's going to wrap this one up. Thanks a lot, guys.